So let's start our OS and then go to populate the Cortex-M port for the Micron kernel. So over here, I'll just come down. This is our main file. I'll just come down here and say OS start, and then it takes an error like this. So this time we've started our OS. And then I'll just open here our assembly file. We wrote the assembly code for porting in the single app, and the single task application is exactly the same. There's nothing we need to change, so I'll just bring that code here. This is it. And next, all we have to do is just initialize the STM32 timer and the GPIO stuff. So I'm just going to bring that here as well. Bring that down here, and then I'll just take the prototype to the top to keep everything nice and clean. Put this here. And then GPIO init, I'll put it here as well. I'll just forward this. So we can just call this, we can initialize our system clock and then initialize the GPIO in main file. I'll just come here, main, and GPIO init. Right. So what we want to do now, we want to go to the task function of the blue LED, the blue LED controller, and turn on the blue LED, and then do the same for the other tasks. So we start with the blue. I'll just say how GPIO write pin turn the blue LED on, basically. So I'm going to come here and do that like this using the HAL API, how GPIO write pin, and the blue is on port D, pin 15, and GPIO pin set means just turn the pin high. And we do the same for orange. Orange is on pin 13, and then we can do the same for red. Like this. Red is on pin 14. So this is it. So I'm going to set my debug options, ST-Link debugger, and then reset and run, and then OK, and then OK. I'm going to rebuild my project. And I'm going to click here to download onto my board. And as you can see, there's something fascinating happening. Only the blue LED is on. We've told all the task threads to turn on their LEDs. They all have the same priority, but just one is turned on, the blue. And the reason why this is, I'll just post a video and give you the chance to guess why just the blue LED is turned on. Right. So what's your answer? Okay, let's see what the right answer is. So we're running a preemptive scheduler here. It's not round robin. We've not initialized round robin. And round robin basically means time slicing, meaning one task runs for a while and then another task runs and then the next one runs. The process I shared among the tasks, one after the other. We don't have that here. We have preemptive scheduling here, and preemptive scheduling tasks are driven by event most of the time. So currently we've got all tasks set with the same priority. The rule is the task with the highest priority always runs. And this is summarized in the phrase, the most ready to run tasks always run. And the most ready to run task is the task with the highest priority among the tasks. And this task must have the highest priority, and this task must not be waiting for a resource. So if the task is waiting for another resource from another task, it's not the most ready to run task. If the task has got all of its resources and yet its priority is not as high as one other task which isn't waiting for any resource, is still not the most ready to run task. Currently, we have all tasks. None of them is waiting for any resource from any other task. They all have the same priority. Why then aren't they all running? Well, the problem is, because we have a preemptive scheduler, tasks of the same priority cannot preempt one another. So what happens is the first task created runs on the CPU and then it becomes selfish. It doesn't give it up because it was created first and there's no other task with a greater priority to preempt it. It keeps the CPU forever, basically. So if you see the order in which we created our tasks, blue was created first, blue task is created first, hence blue is stuck on the processor and it's doing its work. Another way of viewing this is the infinite loop here. Remember, tasks run in an infinite loop. So blue came in and then he entered a while one loop and then he started executing this. The only way blue is coming out of this infinite loop is when a higher priority task is called and then blue can be pulled out. But all the other tasks have the same priority, so it keeps running the code in this infinite loop. So to test this, what we're going to do is we're going to change the order in which we created our tasks. Basically, I'm going to cut this. I'm going to cut the OS task create for red LED controller task and then put it at the top so that red becomes the first task we created. So I'll put this here and I'll rebuild and I'll download onto my board. And as you can see, only red is on and red is stuck with the processor being selfish with it. So this is very fascinating. This becomes a first come first serve approach when all tasks have the same priority. So what I'm going to do is we're going to save this project and create a copy of this project and run more experiments to see how tasks interact amongst themselves. So I'm going to save this and I'm going to recreate a new one. So I'm just going to press Ctrl S and then I'll go to the folder where I keep the project.